In this lesson, we're going to extend our treatment of complex equilibrium solutions by considering the acidity of salt solutions. Now, at first, this may seem to be a strange topic to undertake because we're not normally used to thinking of salts as being acidic or basic, but we'll see that under the right conditions and the right choice of salts, in fact, we can cause solutions to have acid-base properties. Our learning goals are, first of all, to say, can a salt be a solution, an acidic or a basic solution? And I'll even go a step further to say a learning goal is, can we predict when it will be one or the other, or neither? Let's start off by defining what a salt is. And I mean to define this not as what you eat with your food, but in more general terms. A salt is basically a compound, an ionic compound, that is created when we have an acid-base neutralization reaction. So we combine an acid, we combine it with a base in aqueous solution, and what we'll generally create is a salt, which is some ionic compound, and water. So a good example for this would be, for example, the mixture of perchloric acid, HClO4, with lithium hydroxide to form lithium ions, perchlorate ions, and water. Now, I've purposely left the lithium ions and the perchlorate ions as separate because they do remain as an electrolyte solution. But each of those ions themselves may have acid-base properties, as we'll soon discover. So it's important to recognize what it is you have in your solution and that you are creating these ions in solution. I think it's really important to recognize when you have a particular salt, like in this case the salt is basically lithium perchlorate. Where does that salt come from? What kind of acid-base reaction does it come from? Well, if you take the cation of the salt, the lithium plus ions, that had to come from the base. That had to be the cation that was attached to the hydroxide in the original mixture. In this case, that's the lithium ion. The anion, the perchlorate ion, is what was combined with protons, or H plus ions, in the original acid. So the base tells us what the cation should be, the acid tells us what the anion should be. So anytime we're given a salt, we can reconstruct the acid and the base that had to be together in the neutralization reaction by simply recognizing that fact. We would combine the cation of that salt with hydroxide, and we would combine the anion with H+. Let's consider some specific examples so that we can see how this business of creating salts can lead to acidic or basic solutions. Let's first start with a strong acid, strong base combination to produce a salt and water. Now I'll remind you that we have both acid dissociation reactions and base reactions with water that have these forms. The acid can react with the water to form hydronium ions in solution along with the conjugate base A-. The base can combine with water to form BH+, a protonated base, and OH- in aqueous solution. Now if these were a weak acid and a weak base, both of them would have equilibrium constants less than 1, which means that these reactions would favor the left-hand side. If they're strong acid and strong base, then they're typically going to favor the right-hand side, so they will have a different property, an acidic base property, in solution. So let's look at a particular example. We've already seen the combination of perchloric acid and lithium hydroxide. If I were using those in this strong acid, strong base combination, I would find that in fact that the Ka for HClO4 is 10 to the 8th. So in other words, if HA were perchloric acid and it's combined in water in a water solution, then it goes very strongly to the right-hand side. It really produces a lot of hydronium ions and conjugate base ions. On the other hand, lithium hydroxide, when it's put into this situation, if it's thrown into water, it would have a Kb of about 2.3. It's not quite as strong, obviously, as perchloric acid is strong as an acid, but it's still favoring the product side, so it's still considered to be a strong base. So the relevant reactions that we want to think about are what happens to those ions, the lithium plus ions and the perchlorate ions, once they get into solution. Does the lithium ion react with water to form lithium hydroxide and hydronium ions. If it does, then it is an acid, okay? Now it turns out that when we compute what the Ka value for a lithium plus should be, we can relate it to the Kw and the Kb for lithium hydroxide, and what we find is that in fact the Ka for lithium ions is only 4.3 times 10 to the minus 15. Okay, a very small pKa, a very small Ka value for lithium ions means that this reaction would not go very strongly to the right. In fact, it would mostly be on the left. Lithium ions do not have strong acid properties when put in aqueous solution. If we look at perchlorate now, the second reaction, perchlorate ion reacting with water to form, again, undissociated perchloric acid and hydroxide ions. Well, once again, we can find out what the Kb, because this is a Kb reaction, we can figure out what the Kb should be for the perchlorate ion. And again, we find it's really small, 10 to the minus 22. Basically, only one molecule out of, or a couple of molecules out of each mole are actually undertaking this reaction. So neither lithium plus nor the perchlorate ion are really generating hydronium ions and hydroxide ions in solution. They do not have very strong acid-base properties. So this is what defines basically a neutral salt. A neutral salt is one whose cation and anion have very small Ka and Kb dissociation equilibrium constants when they're put into aqueous solution. So because they do not produce hydronium ions, they do not produce hydroxide ions, they have essentially no acidic base properties once they're put in solution. So they are neutral as a salt. Now let's move on to weak acid neutralization. So this may be a different story. When we consider adding a weak acid and a strong base together to make a salt in water, okay, again, I won't specify a particular one, but our weak acid might be HA, our strong base might be MOH. We're going to produce a cation and an anion, from the cation from the base and the anion from the acid, M plus and A minus. So what we're going to be interested in are the acid-base properties of the M plus ion. Does it have acidic properties, or does the A minus ion have basic properties? So to examine this, let's consider nicotinic acid. Nicotinic acid is actually a more fancy name for niacin or vitamin B3, which you may take as a supplement if you take vitamins. And its reaction, the neutralization reaction, looks something like this. C5H4NCOOH is nicotinic acid, has a Ka of 1.8 times 10 to the minus 5. KOH, we've already seen, it's a very strong base. It essentially completely dissociates in water. So when these two react together, you will have potassium ions, which are the hydroxide cation. We'll have the nicotinate ions, which are the conjugate base of nicotinic acid. And we'll have water. Okay, that's what's produced in this reaction. So what we'll want to know is something about the properties of the K plus and the nicotinate ion in terms of whether they show acid or base properties. Now, K plus, as you might expect, I hope, does not have a measurable effect on acidity or basicity. When we write out its acid reaction, its acid dissociation reaction, Ka for K plus, again, it's going to be the autoionization of water equilibrium constant divided by the Kb of KOH, and we're going to get a really small number, 2.0 times 10 to the minus 15. This is not a very acidic cation when we put it in aqueous solution. Nicotinic acid, though, on the other hand, nicotinate ion reacting with water to give undissociated nicotinic acid and hydroxide ion, this is going to have an equilibrium constant of about 5.6 times 10 to the minus 10. Now that does seem pretty small, but remember it's greater than the autoionization of water. So in fact there is some of this that happens. There is some of this that's going to affect the pH of the solution. All right. In fact, what this allows us to do is to define this as a basic salt. It is a salt where the cation that comes from the base, strong base, has no acid-base properties, but the anion that comes from the acid undergoes this weak base reaction when it's in water to form hydroxide ions, to some small measurable amount. So whenever we mix a weak acid with a strong base in a neutralization reaction, we're going to produce something called a basic salt. Now, I'm showing you here the titration diagram for a weak acid titration to remind you that when we get to the equivalence point for this titration, that's basically when we have all of the acid, all of the weak acid, has been converted into its conjugate base, or A-. So at the equivalence point, the only thing we have in the solution really is A-, the conjugate base of the weak acid. Notice where the pH is. The pH is above 7. So that stuff in solution creates a basic solution. And that's why salts that have that particular anion in them will form a basic solution when they are in water. Now let's consider a weak base neutralization. So we're going to put the shoe on the other foot. We're going to have a strong acid and a weak base combining to make salt and water. The general reaction, I'm going to draw a generic weak base as an amine, so an amine from organic chemistry. And the strong acid could be, whatever strong acid you like, hydrochloric acid, nitric acid, whatever it needs to be. In this case, when we create the neutralization reaction, we're going to create a conjugate acid, which is going to be the protonated base. So we're going to add a proton to the base to make RNH3+. And then the anion is going to be the anion from the acid, which will be the conjugate base for that acid. So this is the net result of this neutralization reaction. Now, I've introduced something new here, this concept of protonated amine. Now, this is just a fancy way of saying I've taken an organic base and I've attached a proton to it. So in this case, when we have an amine as our organic base, when we attach the proton, it's going to attach itself to the same nitrogen that forms the amine. So we end up with an NH3+ attached to an organic compound of some kind. Now, as our example, I'll use ethanolamine, which is basically ethanol, stuff that's in alcoholic drinks, with an amine attached at the other end of the compound. So it's got both an alcohol and an amine group in it, and we're going to see how that neutralizes with hydrochloric acid. So when we combine these two, first of all, ethanolamine has a Kb value of 3.16 times 10 to the minus 5, so it's, as weak bases go, reasonably strong weak base. These things will combine to form the protonated ethanolamine, which is OHO C2H4 NH3+, and the acid anion, which in case of hydrochloric acid is just the chloride ion. Now, as we found before with the strong base, the chloride ion does not have a measurable effect on acidity or basicity, and this is why sodium chloride, for example, is not going to make for an acidic or basic solution when you put it in. It's not going to taste good if you make salt water, but it's not going to be acidic or basic. Chloride ion, when it undergoes its basicity reaction, would form undissociated HCl and hydroxide ion, but the Kb for this is, again, really, really small. It's about 5 times 10 to the minus 22, so if you put a mole of chloride ions into a liter of water, you would turn 10 of them into hydrochloric acid, and the rest of them would be remain as chloride ions in the solution. So not very likely to happen. What about the conjugate acid? Okay, so here is the protonated amine, ethanolamine, and when it's thrown into water, it has the possibility of creating, again, regenerating the regular ethanolamine and producing hydronium ions. The Ka for this process is 3.16 times 10 to the minus 10. So even though it's not a very strong acid, it is nevertheless an acid that's created here. So what this has done is basically create a situation where combining a strong acid with a weak base will produce an acidic salt solution due to the acidic activity of the protonated base. Once again, we can draw analogies to a titration reaction. This is one that we haven't looked at in the titration thing, but it is a strong acid, weak base titration. In this case, we're starting off with a weak base solution. We're adding a strong acid to neutralize it. So it's basically flipped upside down from the weak acid, strong base titration. Once again, we find that when we have the acid that is conjugate to a weak base as the only thing that's in solution, as this is where the equivalence point is on this titration curve, it has a pH lower than 7, which means that it is slightly acidic. So conjugate acids of weak bases do form acidic solutions when put into water. And so this particular combination of a strong acid and a weak base make for an acidic salt solution. So this is a sort of a brief summary of where we are right now. When we combine a strong acid and a strong base, neither one produces an ion that has much in the way of acid-base properties, so it forms a neutral salt. When we combine a weak acid and a strong base, it's the conjugate base of the weak acid that causes the solution to be a basic solution. The strong base components do not have any role in the acidity or basicity of the solution. And finally, for a strong acid-weak base combination, we form an acidic salt because it is the protonated base that is weakly acidic in the solution. The strong acid components don't have any effect on the acidity or basicity of the solution. Now you may be asking yourself, why don't I see a line here for weak acid and weak base? Well, the truth of the matter is that a lot depends in those cases. Is the weak acid stronger than the weak base? Is the weak base stronger than the weak acid? Because this case is perhaps the least predictable of them, there's no strict guideline that we can go by, and therefore probably no exam questions that I'll ever ask you about a weak acid, weak base combination to make a salt. These are the ones that you really need to be aware of, and all of them include at least one component that is a strong acid or a strong base. Just to remind you, these are the strong acids, okay? There are certainly more than this, but these are the common ones that you're going to run across in most situations in life and in the environment. And these are the strong bases. So they're basically the hydroxides of various metals, mostly alkali metals and alkaline earth metals that dissociate readily in water, so they form hydroxide ions when you dissolve them in water. All right, there really are not any strong bases that are of the organic type, that is an amine or an alcohol or anything like that. Those are all weak bases. So let's practice our knowledge a little bit with some examples. Okay, so the whole idea here is that we want to take each of these salts and look at the neutralization reaction that forms them, characterize the components in the neutralization reaction as being either a strong acid or strong base, and then from that knowledge determine whether this forms a salt that is acidic or basic. So I've already done part of the work here. I've included the neutralization reaction because this is something that takes a little while for you to develop sufficient expertise to do. But if I have KBr, that means the K had to come from the hydroxide and the Br had to come from the acid. So I would have KOH plus HBr as the combination that forms KBr. Now, from that, I might recognize that KOH was one of those strong bases. HBr actually was one of those strong acids. So I've got a strong acid and a strong base. We know that when we have both strong acid and strong base, we end up with a neutral salt that comes out of that. Let's go down to sodium formate. So once again, the sodium comes from the hydroxide and the formate part comes from the acid, so it's formic acid. So if I combine sodium hydroxide with formic acid, the sodium hydroxide I hope we recognize as a strong base. The formic acid, ant stings, that's a weak acid. So I have a weak acid and a strong base. Whenever we have a weak acid, the conjugate base of the weak acid forms a slightly basic solution. So it should be basic. For cesium citrate, again, this is pretty exotic. Probably not much cesium citrate sitting around on the planet Earth. But that would come from a neutralization reaction between cesium hydroxide and citric acid. Citric acid is a weak acid. Cesium hydroxide, again, is a strong base. So it's the same combination that we had just above that. So again, we should have a basic acidity. If barium perchlorate was my salt, I would have that come from barium hydroxide and perchloric acid. Well, we've already talked about perchloric acid being a strong acid. So is the barium hydroxide a strong base? So once again, we're going to end up with a neutral combination out of this, so it's a neutral salt. Finally, we'll have methylammonium chloride, so again, a fairly exotic formula. This is going to come from the combination of methylamine and hydrochloric acid. I wanted to show you this because this is a good example of an organic weak base being combined with a strong inorganic acid, hydrogen chloride, to form a salt. So methylammonium chloride is the combination of a strong acid with a weak base. So the common wisdom here is that that conjugate acid of the weak base is going to itself be an acid, a weak acid. So this will form an acidic salt. I hope this makes sense. You may want to review this slide again and see if you can come up with the same reasoning so that you can predict the acidity or basicity of each of these salts. So, have we achieved our learning goals? A salt solution can be acidic or basic. And in fact, if we know a little bit about the composition of that salt, we can also predict whether it is an acidic salt or a basic salt or a neutral salt. Thank you.